Last big section on the rational roots theorem. So if you haven't already done so, please make sure that you watch the first two videos on the rational roots theorem and that you've brushed up on synthetic division. In this section, we're going to be finding all of the zeros for particular polynomials. And what I mean by that is the complex zeros. And if you've forgotten, if it's been a little while, what a complex zero is a number or a zero that would have a real part, like we have been finding, and it could also have an imaginary part. So a complex zero, or all of our zeros, are going to have real and imaginary numbers included. So let's look at an example. Let's say we're going to find all of the complex zeros for f of x equals 3x to the fourth plus 5x cubed plus 25x squared plus 45x minus 18. And if you've recently watched my previous video, Rational Roots Theorem Part 2, you'll kind of know where we get started. You'll recognize the process. The first thing that we're going to do is we're going to list all of our possible rational zeros. Now, I want to remind you what a rational number is. A rational number is a number that can be expressed as a fraction of two integers. So 3/5 or -1/7 or even 5 or the number 0. Those could all be written 5 over 1, 0 over 1, and other integers over integers, positive or negative. But a rational number, the list that we're going to get, it does not include square roots that don't simplify, like the square root of 5. Nor does it include any imaginary numbers. So our rational zeros is a good starting point, but it's not a complete list of all, let's see, in this case it would be 4 complex zeros that we're going to have. So nonetheless, let's get started here. Our possible rational zeros would be plus or minus, let's see, all the factors that go into 18. So that would be 1, 2, 3. 4 does not go into 18, neither does 5. 6 does. 7 and 8 do not, but 9 does. And 10, 11, 12, 13, 14, 15, 16, 17 do not, but 18 does. All the numbers that go into 3 would be in the denominator, and fortunately that's a small list. It's just the numbers 1 and 3. So our possible rational zeros for this problem would be positive or negative. Let's see, let's do everybody over 1 first. So that would be 1, 2, 3, 6, 9, 18. Now let's do everybody over 3 second, making sure we don't include any repeats. So we definitely do not have 1 over 3 or 2 over 3. 3 over 3 is 1. We have that. 6 over 3 is 2. We have that. 9 over 3 is 3. We have that. And 18, didn't make sure I didn't miss anything. 18 over 3 is 6. We have that. So we're good with our list. And then from this list, we're going to pick numbers and we're going to use synthetic division to see when we get a remainder 0. And once we get a remainder 0, we have a hit. We know that we have our 0 for our polynomial. If we get something after we're done with the depressed polynomial or the smaller polynomial that we can factor, then we're going to go to factoring, because factoring is much easier than this. So let's start with the number 1. Now, I'm going to include a couple of incorrect guesses here because I don't want you to think that whenever you're selecting from this list over here, you're always going to get a yes the first try. So I'm going to mix in a few, but I'm going to do this selectively. So we're going to guess x equals 1, and we're going to put 1 in the synthetic division box. And next to 1, we're going to list, let me get my highlighter out, all of the coefficients from our polynomial. So that will look like 3, 5, 25, 45, negative 18. I'm going to go through the synthetic division fairly quickly because by now you've seen this a bunch of times. Bring down the 3. 1 times 3 is 3. 5 plus 3 is 8. 1 times 8 is 8. 25 plus 8 is 33. 1 times 33 is 33. Ooh, these are getting big. 78. 1 times 78 is 78. And negative 18 plus 78 is not 0. We have remainder 60. Which is not good. Okay, if I were a student, I would be checking x equals negative 1 first. But because I am not a student and I have looked ahead at the answer and cheated, I am going to guess x equals negative 2 next. So negative 2 in the box, 3, 5, 25, 45, negative 18. Bring down the 3. Okay, here we go. Negative 2 times 3 is negative 6. Plus 5 is negative 1. Negative 1 times negative 2 is positive 2. 25 plus 2 is 27. 27 times negative 2 is negative 54. Negative 54 and 45 is negative 9. And negative 9 times negative 2 is, yay, positive 18, which gives us a remainder 0. That means a lot. That means that x equals negative 2 is one of the zeros of our polynomial. That also means that we can start using this much smaller polynomial to do our further work. Okay. So let me erase this screen and we'll start from there. Much better. Okay, starting with our newly moved depressed polynomial, let's not forget that our zeros have started with x equals negative 2. And we hope to find 3 more zeros for a total of 4. Now, looking at our depressed polynomial here, generally I like to get 3 terms, not 4 terms, but look at this. If this is our remainder, that means this is our constant term. That means the 27 is the coefficient of our x term. It's a positive. The negative 1 is a coefficient of our x squared term, and the 3 is the coefficient of the x cubed term. What I want to bring your attention to is that's factorable by grouping. And if I can avoid using all this tedious synthetic division, I'm going to do it. So let's factor this depressed polynomial because we have that glorious remainder 0. Factor this by grouping. So grouping together the first pair, we're going to factor out the x squared, leaving us with a 3x minus 1. Bringing down the positive sign and looking at the second pair, there's a common factor there of a 9. Factoring that out, it again leaves us with a 3x minus 1. So what we have is 3x minus 1 is a common factor, and x squared plus 9 is left over. Okay, here's what that means. That means, if you remember from the previous video, that we can factor our gigantic polynomial from way up here, which I won't rewrite, I'll just call it f of x. We can factor that using x equals negative 2, so x plus 2, and using the factored version of the depressed polynomial, or the rest of it. So 3x minus 1 and x squared plus 9. Now, if you're tempted to factor the x squared plus 9, don't forget that's the sum of 2 squares, not the difference, not subtraction. So x squared plus 9 does not factor. But here's what you can do. This is a factored version of f of x, and to find all of your zeros, you can take each of these factors, set them equal to 0, and solve. Here's where we get the x equals -2 that we already knew about. If we add the 1 and divide by 3, we get x equals, not that, 1/3. And if we move the 9 over and then square root both sides, not forgetting about our plus and minus sign, we have x equals plus or minus 3i. Okay, that tells us what all 4 of our zeros are. -2, positive 1/3, 3i, and negative 3i. So if we had to find all of the zeros for that polynomial there, we would have 4 of them, just like the exponent suggested at the beginning. -2 we got from doing synthetic division. 1/3 we could have got from synthetic division, but we finally got factoring. And 3i and negative 3i did not show up in our original list of possible rational zeros because rational numbers don't include imaginary numbers. So here's a really powerful thing that we can use this for. We've found all of our zeros, which is really helpful. We can also, like in the previous video, factor. So here's how we can factor f of x yet again. Instead of factoring it like you might have here, we can factor it like this. X minus 2, x minus 1/3, x minus 3i, and x plus 3i. The only thing that I'm missing is some leading coefficient here that we usually write as a. With a little bit of algebra, I could figure out what that a is. I'll tell you, for the curious in the group, it's 3. But for the sake of your homework, you're going to be writing it as just an a in this case. So there's a completely factored version of f of x. There we go, much better. This result leads us to 2 very, very helpful theorems in calculus. Here's the first theorem I'd like to point out. It's called the fundamental theorem. I'm going to use that abbreviation for theorem of algebra. And what the fundamental theorem of algebra says is that if x equals, I want to use a letter. I don't want to use 2, 3, or 4. I want to use a letter. So let's call it root. So we'll do little r for a root. Remember, the roots and the zeros mean, and the x-intercepts mean the same thing. But I want to have several roots. So I don't want to call them r, r, r. That gets confusing. So r1, r2, r3, let's say r4, and so on. So if we have, in this case, let me erase that last part. If we have 4 roots, let's say, for a specific polynomial, so r roots of the polynomial f of x, then we can write f of x equals some leading coefficient, whatever that might be, we usually use a, times x minus r1, x minus r2, I'm going to run out of room, x minus r3, and x minus r4. Oh, I don't know how to move things. Oh, no. Move this. Oh, that's not good. Let's just write it a little bit down below. There we go. X minus r4. So we can write x minus each of the roots as a factor of f of x. We couldn't have written that previously because some of our roots might have been imaginary numbers or just non-rational numbers, maybe the square root of 2. So, fundamental theorem of algebra says that if you can find all of the roots for a polynomial, you can then factor that polynomial even if your roots are imaginary or irrational. The second thing that I want to point out about this is called the conjugate pairs theorem. And that theorem says, here, look at this. That theorem says, if you know that one imaginary number or complex number is a root of your polynomial, then you know his conjugate, which means change the sign on the imaginary part. His conjugate is also a root. So if I were to write this out in theorem form, if x equals a plus, let's say, bi is a root of some polynomial f of x, then its conjugate, x equals a minus bi, is 2, a root. So if you know one imaginary or complex number is a root, you automatically know a second root. You know its conjugate is also a root. Let's do an example where we use that conjugate pairs theorem. Okay, let's say we're going to change the question just a little bit. Instead of finding the roots or factoring, let's go the other way and find the polynomial. So let's say that we need to find a polynomial of degree 3 with zeros, 2, I don't need a comma, well, that's fine, and 4 minus I. Okay, first part. Since x equals 4 minus I is a 0 or a root, so must x equals 4 plus I, or its conjugate, be a root. Okay, so here's what we have. Let's see, degree 3. If you have degree 3, you're looking for 3 roots or 3 zeros. And sure enough, we have 3 now. 2, 4 minus I, and 4 plus I. So here is how we can write our polynomial. They didn't give us enough information to figure out what our leading coefficient is, and it just said to find a polynomial of degree 3. So I'm going to leave the leading coefficient as a. If x equals 2 is a 0, then x minus 2 is a factor. If x equals 4 minus I is a 0, then x minus 4 minus I is a factor. And finally, if x equals 4 plus I is a 0, then x minus 4 plus I is a factor. If you want to, you can distribute the negatives through the second two, but we are pretty much finished. X minus 2 times the a, x minus 4 plus I, and x minus 4 minus I. Now, depending on how far the question that you're working on needs you to go, sometimes you might actually have to FOIL or multiply that beast out. But that's for a different video. A bit lengthy, but not challenging, not hard. So for the sake of this, the purposes of this video, I'm going to leave it in the factored form, but you could distribute and multiply it out if you had to. I would prefer to do a couple more examples. There we go. Let's find a polynomial of, let's say this time we have degree 4 with zeros, x equals negative 3. I'm going to tell you that negative 3 has a multiplicity of 2, and x equals 5i is another 0. Okay, so now for starters, if we have degree 4, we're hopefully looking for 4 zeros. And I can see 2 of them pretty clearly. So we would have x equals negative 3 and x equals 5i. And just like in the last example, there's a complex number, an imaginary number, so its conjugate, negative 5i, must also be a 0. And I want to talk about multiplicity. I talked about it a little bit in the rational roots theorem part 2, but what multiplicity means is this. Multiplicity means that x minus a negative, or x plus 3, shows up twice as a root. You can think of it as x plus 3 squared, or x plus 3, x plus 3, to see those two roots. So I technically have 4 roots here for my degree 4. It's just that one of them, because of its multiplicity, or how many times it appears, one of them appears twice. So here's how I can write my function. This again just says to find any polynomial, so I'll make our leading coefficient a. X plus 3 squared, because it has multiplicity 2, x minus 5i, and x minus a negative, or x plus 5i. And I'm done. Let's do one last one, and I think I can fit it on this same screen. Same question. I want to tell you that the degree is 5 and that the zeros are x equals 1 with a multiplicity 3 and 1 minus 2i. Okay, so if I have a 0 of x equals 1 with a multiplicity 3, I have x minus 1 showing up 3 times. Furthermore, if I have 1 minus 2i as a 0, I have 1 plus 2i, its conjugate, is a 0. Now, including multiplicity, if you count all those, 1, 2, 3, 4, 5, we have our 5th degree. So we can write leading coefficient is a, x minus 1 appears 3 times or has a multiplicity 3, x minus 1 minus 2i, and x minus 1 plus 2i. And there is a polynomial of degree 5 with 1 multiplicity 3, 1 minus 2i, and its conjugate 1 plus 2i as all of the zeros.